Hi, in this video we are going to do inverter layout using Magic Tool and do DRC, LVS, parasitic extraction, and also post layout simulation. Um, I might divide this into two parts. In the first part do the layout and the next part do DRC, LVS, parasitic extraction, and the layout simulation. So let's start with the first look at the inverter schematic. So my inverter schematic is inside project test, and inside here I have inverter test bench. Let me look at the schematic first, inverter schematic. So the length is 0.15 micrometer and the width is 1 micrometer. Both, this is same for both NMOS and the PMOS. And in our previous videos we did create a symbol for the inverter and simulated. That's gonna be inverter test bench. I would like to quickly review what the netlist look like for this schematic. So if you did netlist and then go to edit netlist, so the netlist looks like this. So we have these two devices, and the pin order is drain, gate, source, and the buck for the NFET, and for the PMOS, same order, drain, gate, source, and the buck for the PFET. One thing we can noticeably here, one thing is noticeably here is the length and the drain are numbers. Sorry, length and width are the numbers, but other parameters like the fingers, this is also number, but the area of drain, area of source, and the perimeter of the drain and the perimeter of the source are some parameters. This is what different from the layout netlist. Later we are going to see. And when we do the LVS, just keep in mind that the layout netlist and the schematic netlist is a little bit different. And if we did the netlist for the test bench, it's include all the stimulus for the pulse power supply, and the X1 on the top, which is this X1 inverter. And inside subcircuit we have these two MOSFET transistors, which is the same as the schematic netlist that we just saw. Let me just simulate quickly, and keep in mind that the simulation results are stored in this directory .xscheme simulation and inverter test bench.raw, this file. And this is very important for keep in mind that when we do the post layer simulation and also the schematic simulation, when we compare, we are going to extract the plottable data from these files, and we will compare the schematic and the post layer simulation results. So this is the inverter simulation. Okay, now let's start doing the layout. Before that, I'm going to create a layout directory and then go to layout. Just type magic to invoke the magic tool. So it invoke two windows. One is where we draw the layout, another window is for the command, for the inline command. Here, before we start, from the options tag manager, we need to choose technology as Sky 130A, and as you notice on the right column, all the layers appeared here. And then in order to draw the layout easily, we're going to do set the grid to 0.05 micrometer. So one grid is 0.05 micrometer. In our schematic, the length is 0.15 micrometer. So 3 grids will be equal to 0.15 micrometer. And we need to also do snap the grid on. So when we choose the box, we cannot choose in the middle. It's just snap to the grid. And we do Z on the keyboard to zoom in and Shift C to zoom out. Whenever we choose, we draw the layout. So left click on the left bottom corner and right click on the top right corner to choose this box area. And inside this box area, we're going to choose the layers. For this one, we need to click the mouse middle button to draw inside this box. For example, if I want to draw the polysilicon, which is the gate of the MOSFET, middle click, it appears here. Another way to do is, if I click somewhere else, the box area is the same. And if I do paint poly, it paint the poly here. And usually what I see from the tutorials that we need to do DRC complete to see the real-time DRC violation. But even if I didn't do that, maybe the latest version no need to do that. But anyway, for enable that feature, we can click on this DRC complete. So as you can see, when I draw the poly here, we white dots appears here. That means that there is DRC violation. And in order to see this DRC violation, we need to choose the area. So left click, right click to select the box, and then write DRCY. It's going to tell what's the DRC violation here. And it says the policy spacing should the violation is policy spacing is less than this amount. So because we have 4 grids here, which is the 0.2 micrometer. So let's say I want to move this poly to right side. Select the box. And I need to select the area to select this polysilicon first. And then move to east by 2. It moved 2 grids to the right. Now you see that white dots are gone. So that means that there's no DRC violation. And another quick way to draw the layer is if I choose different box area and then come back to here, mouse middle button. It's going to draw the polysilicon, the same layer in the box. And if I want to delete this polysilicon area, then type erase poly. Whatever the layer I want to delete, keyword is erase and poly. Alright, so I'm going to erase this one as well. Instead of typing, just like a Unix command, last command upper arrow on the keyboard, erase poly. It's gonna erase the poly. And then we already draw this polysilicon area here. And if I would like to know the what's the length and the width of this polysilicon area, then just click B on the in the keyboard. It's going to show us the length, currently 0.15 micrometer, and the width is 0.25 micrometer. And it's scaled to some lambda value, which is 15 and 25. But for now, we just need to look at this one. Or if you are more comfortable with lambda, then it's up to you. So in the schematic, we have 0.15 micrometer, but the width is 1 micrometer. So the widths are a little bit longer. So I'm going to left click and then right click to make it wider. And then in the same time, if I click B, so right now it is 0.9. So I need to choose more. Okay, now it's 1. Now the same as schematic length and width. Now mouse middle button, choose all the box area as polysilicon. Now we need to do NMOS first, so let's do the diffusion. That means we need to do N diffusion here. In the same time, let's click B. So the area is now 1.35. Let me do 1.3. For the series layout, we should do the same space on the left and the right, but for this tutorial, we just need to familiar ourselves with the process. So I'm not going to go into too much detail. I'm just roughly draw the layout, and we're gonna go through all the layout process. And then we can choose N diffusion, middle button, choose the N diffusion. And as long as I draw the N diffusion, you see that there's a DRC violation. Again, choose the area and DRCY. So poly overhang of transistor currently is less than this one, so I need to extend the poly by at least 0.15. So that means that 3 grids is enough. And let's look at here. So if I paint poly, you see that the DRC violation is gone now. The same thing for the bottom part, and paint poly, now it's gone. Now we still see some white dots here, so DRC violation, DRCY, we see that N diffusion distance to P tap must be less than this. That means that we haven't drawn the P substrate yet. So for now, let's ignore this DRC error. Now I need to do a metal contact to this N diffusion. But before that, we need to look at first the process stack up. So if we go to Skywater 130 nanometer from the design rules criteria, process stack up. So we have this transistor, which is we have this diffusion have a contact connected to this metal. This metal is local interconnect metal, and then on top we have this metal contact connects to metal 1, and so on to metal 5. So for this N diffusion, we need to draw local interconnect metal and then do the contact here. So you can see that we can draw the local interconnect is bigger, and then contact is smaller. So I'm going to choose this area as local interconnect. The command is paint local interconnect li. Do the same on the left side. Now I'm going to do local the contact to the end diffusion. So that's gonna be paint and diffusion contact. These layers we can also choose from the right, for example here, and the contact and diffusion contact. For the command is paint and DC, and do the same on the left side. All right, so now we connect this local interconnect metal to the end diffusion through this contact. Now shift mouse middle button. If we scroll the mouse middle button, it's left, right, horizontal move, and then I need to do P substrate, draw the P sub for this NMOS transistor. This box I'm going to paint. That's going to be P substrate diffusion, and then I'm going to make the same local interconnect, and then do the contact. So that contact will be, because this is P substrate, so that's going to be P substrate contact PSC. Now you see that how the DRC violation is gone now. So if we select the area, left click, right click, and DRC no errors found. Okay, so our NMOS transistor is done. Now we need we can copy this shape and do the PMOS. So before that, we select the area. So when we have Shift Z to zoom out, if we just select this area and then click Control Z, it's going to be zoom into this box area. And in order to copy these layers, we need to first select area, and then we're gonna copy to where we're gonna go up, that is the north, to 30. Now here in this window, if I zoom out, so now we copy the exact same, and the magic is there's easy way to change NMOS to PMOS. That is, if we just because right now the layers are already selected, so if we just paint NWell, it will automatically change to PMOS transistor using NWell. Now we see that there's a DRC violation here. It's because the distance is small, so you can check again the same method, select a box area and the DRCY. So I'm just move this to move. First let me select the area and then move north by 2 grid. Still DRC area. I'm going to move it again by 2. Now you see that DRC is gone. Now we see a little bit white dots here, most probably because the NWell, DRCY, NWell overlap, NWell. So the P diffusion here, so okay, we need to extend this one. Let me select this area. For this one, I'm going to paint NWell. Now the DRC is gone on this side. What about here? And we'll overlap of and tap. Less than this one. I think this one is also because the extension is not enough. Paint and well, okay, now DRC is gone. Just to make sure that whole area DRC is DRC free, DRCY, there's no errors. Okay, good. Now we need to connect these two transistors. Their gates are connected, so the poly, select this area. I'm going to paint poly to connect them, and the drains are connected together. So here I'm just using white metal for this box. I'm going to choose paint local interconnect, and we can actually also connect to metal one, but again cover this area using metal one, and then metal one contact to the local interconnect. For this tutorial, the purpose is to familiar with the process, so I'm not going to draw the metal one. Everywhere I'm going to use local interconnect metal. And so the drains is over output, so here I'm going to paint local interconnect. There's a DRC violation, most probably is the width, most probably is the width, so I'm going to choose a little bit larger. Okay, now this is going to be our output. Now the input, the optimal way to draw the input should be here in the middle. So the distance, the signal coming from here to distance to the PMOS and the NMOS should be the same. Let's try that one. So let's draw here, because I'm still need to draw the poly contact here, but here the distance is so tight. I hope that it does not give me a DRC error. So here I'm going to paint poly. Okay, we already have error here. For the quick process, I'm going to just draw it from here, make it as large as I want. Here, paint poly, and then I need local interconnect on top of that. Then I need to choose local the connect from local interconnect to poly. That's gonna be paint poly contact. Okay, DRC error. Okay, most probably the area. So DRCY. The poly contact width should be more than this. So that means that we need to choose at least 4 grids. 4 grids. Here 4 grids. Here 4 grids. But again, it should be. What I'm going to do is I'm going to delete everywhere from here. Erase poly, erase locally connect. I'm going to make it bigger. Paint poly, paint local interconnect, and then 4x4. I'm going to paint poly contact. Okay, no error now. Okay, this is going to be input, output. Now the one last thing is the source of PMOS should be connected to the bulk. As in our schematic, the source should be connected to the bulk and the VDD. So the optimal layout should be like using a higher metal layer for the power supply. But again, for the purpose of this video, I'm just going to use local interconnect to make them connect. Same thing is here. Paint local interconnect. So what you can do is like cover this area, use metal 1 and then metal 1 contact with the local interconnect. For me, I'm just going to connect just using the local interconnect. Okay, now if I shift Z to zoom out and then control Z to area, and then we can type S to like one thing to select everywhere that connected is mouse hover over, and then if we click S, it's gonna be select all the connected area. Okay, so if I click somewhere else and then S, it's gonna be select all the area. Control Z, zoom to the box area, and then I'm going to save it. Oh, okay. One thing we didn't do the port, but anyway, let me save it first. Save inverter. Okay, now we need to do the ports. Now there's a little bit trick on the ports, so we need to make sure that the port, the order should be the same as schematic, because we're gonna do LVS. Otherwise, the LVS gives error. So in the schematic, if we do, we have already done the netlist. If we check the netlist, drain, gate, source, drain, gate, source, and since and here it commented out the subcircuit. So when we use the subcircuit, when we extract the layout, as subcircuit, so that we can in the inverter test bench, right, we can, if you look at the netlist, we are going to substitute this subcircuit portion with the post layout netlist so that we can run the post layout simulation. So it's better to wait, here is VDD in out VSS. However, in the schematic, okay. Okay, we already opened that one. So so we have two MOSFETs, drain, gate, source, out, in, but here the source is VSS for the NFET, but here the source is VDD. For the layout, I'm going to follow this subcircuit because when we do the post layout, we should follow this one. Let me try that one when we do the port order. Anyway, when we extract the post layout netlist, we can still able to edit the text file to do the netlist if there's some mismatch. Let me close this. That's going to be out. The order is out, in, out, and VSS. When we do the port, what we need to do is left mouse click and left and the right mouse click at the same time. It changed to this plus sign, and here you need to make it label VDD, and the text should be on the west side, and it appears as VDD here. And in order to make it port, oh yeah, one thing. First let me remove this label first. There's one issue here. Erase label, erased. So here, because we have both local interconnect and this and diffusion, another layer, 2 layers. So when we make the label, we have to identify which layer we should make. Is it on the local interconnect layer or is it on the end diffusion layer? So we would like to do on the metal. That's going to be over VDD. So in that case, label VDD to west, and then we have to specify that it's on the local interconnect. Okay, and then we're going to make it port, make the first port, and it turns blue. That means that we make this port. And then let's do it on the input. Left and right mouse click on at the same time. That's gonna be label in west on the local interconnect, and the port make 2. And then on the out, since here we have only local interconnect, no need to identify which layer. Label out. This time let's put the letter on the east side. Okay, and then port make 3. And then last thing is VSS. Label VSS west local interconnect, make port 4. Oh, sorry, it should be port make 4. Okay. Let's save it. Unfortunately, this label is really small. I believe there must be some setting up for this one, but I'm not sure right now. Let's keep it this way. Out. All right, that's our layout for the inverter. And in the next video, we are going to do the DRC, LVS. No, the DRC should be clean here because we already do it on real time. So if we do here DRC update, there's no DRC error. So in this box area, there's no DRC error. DRC report, DRC complete. Okay. So in our next video, we are going to do LVS, parasitic extraction, and post-layer simulation. Plus, you're gonna plot both schematic and post-layout waveforms to see the difference. I'm sure the difference is very small because this is very simple circuit inverter. But when the schematic is become complex, then there's significant difference between post-layer simulation and schematic. But we can still able to see some differences in schematic and post-layer simulation. So thank you for watching.